I had no expectation that, or even particular drive to be at NASA. My whole life, like from when I was a little girl, I was really interested in science, really interested in understanding how the world worked at a very fundamental level. So it was obvious that I would do a set of A levels that were tilted towards maths and physics, and either physics or maths was an obvious thing to do at university. And I didn't really know then whether I wanted to move towards astronomy or astrophysics or particle physics, and I moved towards an area which is where those two fields intersect. It's currently called astroparticle physics. So I did a PhD in Dublin. I moved following my PhD to the US, where I worked on developing an observatory, an unusual kind of observatory. We were converting an old alternative power source experiment into a novel kind of gamma ray observatory in Los Alamos, New Mexico. And after a few years of doing that, I was at the point where you would normally sort of think about where you were going to be more long-term in your career. And I'd been for a bunch of interviews at universities for faculty positions, and I realized that I actually preferred the working environment at the national labs, and I thought, well, I'd explore whether there might be opportunities to stay in somewhere like Los Alamos for or Stanford Linear Accelerator Center for a couple of years. And I mentioned this at a meeting, and the next day I got a call from somebody at Goddard Space Flight Center saying, we hear you might be interested in a job with us. And they offered me a job that they basically said, this is temporary. It's, as soon as the funding dries up, that's going to be it. But you will have a lot of scientific freedom while you're here. So it was very attractive because it allowed me to really go and sort of pursue my own ideas. And I was young enough to not care about the future. I mean, I think it's always a good idea to follow what you're interested in. So I took that position. I learned how things in space worked. I became involved with the Fermi Gamma Ray Observatory. They then offered me a permanent position, and I've stayed at NASA ever since, in large part because it's exhilarating to be at a place where you're encouraged to develop scientific and technical ideas, and you're surrounded by outstandingly good engineers who can help you sort of bring those ideas into reality.
Wow, yeah, and my first interaction with you at NASA was when we had a lovely family week's holiday just outside Cape Canaveral, waiting for the Fermi telescope to head off into space, and most of us missed it because the conditions weren't such until after we'd left. But what's it like at a space mission, and what was Fermi doing?
Well, so you were having a nice holiday, but in fact I was quite busy because we were coming towards the end run towards launch, which is largely, at that point, all the hard work is done. So you spend the life cycle of a space project is quite stretched out. So you spend at least a year or two really developing the detailed design of the concept.
Can you hear it?
Sorry. And then for the next few years, you're building the instrumentation. You put everything together, you test it, and after 10 years hard work, you finally get to a point where you put it on top of a large tube of explosives, and you kick it off in an irreversible process, and your baby heads off into space, and it's absolutely terrifying. Because it's the single most, or one of the single most vulnerable points of the mission is launch itself, because rockets do blow up, or they don't make it into orbit correctly. So it's an anxious period where we're double checking that everything looks okay. I mean, I don't think you remember at the time one of the reasons we were delayed was that some of the explosives on the rocket that are designed to abort the launch had been found to be outdated, and we had to sort of figure out, was it okay to continue to launch with those? So it was a panicked week and a half.
But it went up, and you then worked on the sort of what Fermi was doing in space for a number of years. Was there any sort of interesting discoveries during that time?
Well, so let me start by saying a little bit about what Fermi does, because it's a very unusual kind of observatory. So Fermi observes the universe in the highest energy form of light, in gamma rays. And it's quite difficult to produce gamma rays. To produce gamma rays, you have to have a population of particles that are extremely high energy. In other words, you have to have an extreme particle accelerator somewhere in space. So a star just sitting there shining is not going to produce gamma rays. A star being sucked into a black hole will produce gamma rays. A star exploding at the end of its life will produce gamma rays. So when you look at the sky with Fermi, at the sky in the gamma ray range, it's completely different to what we're used to seeing when we just look outside with our eyes. The individual point sources that we see in gamma rays are marking the locations of supermassive black holes in distant galaxies, where material is being sucked in and sort of accelerated towards us in streams of particles moving at close to the speed of light. Or we're looking at extraordinarily highly magnetized, dense neutron stars that, as they're spinning, basically put beams of gamma rays in a sort of very regular clock-like manner. So the bottom line with all of this is, when you look at the sky in gamma rays, you're honing in on some of the most extreme, most energetic objects that we know about in the universe. So everything was interesting. But one of the most interesting discoveries that we had was it was a discovery of a gamma ray burst. Now, a gamma ray burst by itself is a regular routine thing for Fermi. And what a gamma ray burst is a brief flash of gamma rays lasting, from a fraction of a second to thousands of seconds. They were originally discovered by the set of satellites that were designed to monitor the nuclear test ban treaty. But instead of finding evidence of nuclear explosions on Earth, they discovered that, in fact, the universe just provides these things. And a gamma ray burst, when it occurs, is, for those brief couple of seconds, the brightest thing in the universe. So one of the main things that Fermi does was detect gamma ray burst, but we don't really know what powers a gamma ray burst. And one morning, I was sitting at my computer, and I got an email that said, "Wake up! Read this email." And I mean, obviously, if you're reading an email, you're already awake. But in any case, it got my attention. And what this person was saying is, they were from the LIGO collaboration, and LIGO is a gravitational wave observatory. And what they were saying is that they had seen evidence from a gravitational wave signal that the gravitational waves were saying they had seen two neutron stars merging. So what's happening here is you have two essentially gigantic nuclei rotating closely together, merging to form a black hole. And at that moment, it's producing an intense burst of gravitational waves, which is what LIGO saw. But 1.4 seconds later, it produced a gamma ray burst. So in that 2 seconds, we now knew conclusively what powered gamma ray bursts, because the chance coincidence of this gravitational wave signal and the gamma ray burst is, almost impossible to occur by chance. But we learned so much more in that moment. We learned, for example, that photons, the gamma rays, travel through gravitational wells in the same way as the gravitational wave. So we're looking at this gamma ray burst. It's on the other side of our Milky Way galaxy. Our Milky Way galaxy contains lots of matter, so it is a gravitational potential. If the general theory of relativity was not correct, the arrival time of the gamma rays and the gravitational waves would have been different by years. So we've immediately have a very new sensitive test of the general theory of relativity. And we opened a whole new field, because this is the first time that we've been able to connect the universe as observed via gravitational waves to the universe that we know about as observed through normal photons. So it was a really, truly groundbreaking moment. And it was so exciting. So like I'm hopping up and I'm like, who can I talk to about this? This is fantastic. And I'm bouncing down the corridor and I'm looking for people to talk to. But I work with astronomers, and this was 2 days before the total solar eclipse that was coming through the US. So everybody was out of town and there was nobody to talk to. And I was like, this is like insane. I mean, I eventually found some poor soul that I waxed lyrical to for a while, but it was a very exciting moment.
Well, that sounds really exciting. Presumably something that, as a scientist, you feel really sort of honoured and excited that happened in your career. So you've moved recently on to the Nancy, well, we call it Roman. You've moved on to Roman. Does Roman essentially do a similar thing to Fermi, or what's the difference?
Roman is entirely different. So Roman is more like a normal telescope. It observes in the visible to near infrared. So, pretty much the same kind of light that you can see with your eyes. And what Roman is it's got the same sort of sensitivity and performance as the Hubble Space Telescope, but we see about 200 times the size, the region of the sky. So what that means is that where with Hubble, you decide what you're going to look at and you go and look at that object, you look at that star or that galaxy or that cluster of galaxies. With Roman, what we're going to do is to do a survey. So we're going to map out a large region of the sky with exquisite accuracy and make a map of the positions and distance of galaxies, looking from near to us all the way back in time, so we can trace the structure and evolution of the universe. And what we want to do with that is to understand how our universe has evolved and how the matter in the universe has formed structures from close to the beginning of the Big Bang until the present time.
Wow, how interesting. And who was Nancy Grace Roman?
So Nancy Grace Roman was, well, when I knew her, she was like a very fierce woman. She was the first female executive at NASA. She was the first chief astronomer. She was the first head of space science. So she was the person who kicked off astrophysics and space science at NASA. So people call her the mother of Hubble because Hubble came about because of her advocacy and work and encouragement. But really, she was responsible for most of the other astrophysics and heliophysics, studying the sun type missions. She remained very active, right through towards the end of her life. So when I met her first, she was already in her late 70s, and she was quite a petite woman who liked to knit. So she would arrive at a meeting, sit in the back of the room with her knitting, and look entirely innocuous, but would then ask extremely direct and pointed and spot on type questions, which would very much disarm the speaker if they didn't know who they were talking to.
So you, some years down the line, might be known as the mother of Roman, if Roman is.
I don't think so.
And Roman is due to launch, I think, in 2026.
Yes, in July 2026 is what we're working to at the moment.
And have presumably a lot of the work, well, I know what you do is quite computer based, but in terms of building a telescope, presumably that's quite hands on. Has COVID had a big impact at all?
Yes. So, I mean, every mission has a spending profile, and we're currently at our peak spend right now. So our annual budgets at the moment are about 500 million a year for like last year, this year, and next year. So it's the maximally bad time to have some sort of a delay, because we have, right now we have the largest number of people working on the project. So in in upstate New York at L3 Harris. There's a large team of people who are currently working on the mirrors and the telescope out in Colorado, which is where I am right now. The folks at Ball Aerospace are working on the mechanical structure for the main instruments. At Goddard, where there's large teams working on the detectors and on the spacecraft. And when you the impact of COVID, at least at first order, was to introduce an inefficiency for everybody. So the sort of overall efficiency for continuing to move forward was something like, settle down to 60 to 70% of what it was. But that's a 40% loss on top of a large number. So we have delayed by around 7 months from where we thought we were going to be.
Okay, well, I won't book flights until a bit nearer the time then. So when Roman goes up, whenever that happens, hopefully 2026, what are your wildest dreams do you think you'd just love to discover with this mission?
So the quick answer is I hope I don't know, because the most exciting things that happen in science is when you're surprised by the universe or physics not working the way that you would expect it or the way that you would predict it, which almost by definition means you can't predict it. That if I was expecting to find something, it means that the universe was behaving according to my predictions. So as an example, if you think about what you might expect to happen with the Big Bang. So the Big Bang happens, the universe is expanding out. The only force that we know about that operates at large distances is gravity, and gravity tends to pull things together. So what we would have expected is that the universe is just going to expand out smoothly, or it's going to be contracting. And when we put together an experiment to measure that, what we found was that, in fact, the universe was accelerating. And that was a moment where you completely transform your understanding about how the universe works. So to map that to Roman, what we have is an observatory that opens lots of discovery space. We are going to be observing, no longer just looking under the lamppost, but mapping out large regions of the sky. We're going to be exploring the nature and evolution of the universe from close to the beginning of the Big Bang until now. And it's, for me, the most exciting thing to happen would be for us to be blindsided by something we completely didn't expect. And I hope I have no idea what that is.
Amazing. I don't know if we've got time for just one more quick question, Simon, but I was just wondering, probably the only thing that you've worked on that, I vaguely, well, I don't even know what it is, but I know you work on black holes. How would you describe what a black hole was to a 5-year-old? Just so I can then, when people ask me what you do, I can come up with an answer.
I'm sorry about the noise. Somebody is, I think, blowing leaves or something immediately outside the window. A black hole is where matter has been compressed to such a high density that the gravitational potential prevents anything from escaping, including light. So it's black. But beyond that, what you see from a black hole very much depends on its context. So there's a black hole of about 1 million times the mass of our sun sitting at the center of our own galaxy. And it sits there pretty quietly. The only reason that we know it's there is that we can see stars orbiting around it. But there's other places where black holes are fabulous. Like you can have like a large black hole at the center of other galaxies where material is being swept in and they're enormously bright. So what I like about black holes is the physics of the black hole itself is quite simple, but that the effect it has on the matter around it can be very complex and very interesting and very exciting, because it creates an environment of extreme physics, extreme radiation intensities, extreme energies, extreme acceleration ability that allow us to really probe kind of, right to the sort of boundaries of physics and look for things beyond what we already really understand.
Brilliant, thank you. That's really interesting.
So Maria, thank you so much, and Julie as well. We only have a few more minutes. If anybody has questions, or I should just check to see if anyone's got their hand up. But just to pick up, Julie, on a comment you just made now, you talked about you found the universe is accelerating. What does that actually mean? Sorry, to a layman like me, what the universe is accelerating? What does that mean?
So if you imagine, like in a two-dimensional sense, if you drew a bunch of dots on the outside of a balloon, and then you blew up the balloon steadily, every dot is going to be moving away from every other dot. And that's what we mean by expansion of the universe. So when the universe is accelerating, it really means that instead of blowing that balloon up steadily, it's started to be blown up faster and faster, closer to recent time. So we can map this, the expansion of the universe out as a function of time. And we find that the universe was expanding relatively evenly up until in cosmological times fairly recently, and has then started to accelerate and expand faster and faster and faster. And we don't really understand why. We give the property that causes the acceleration a name called dark energy, but we don't really know what dark energy is. In fact, that's one of the questions we're hoping to address with Roman.
Okay, thank you. And Ian, I'm going to ask you to come in. Here's Ian from Lausanne. Can I ask you to unmute, Ian?
I am now unmuted. Yep.
Yep.
Thank you very much. Lovely. So I did a bit of science at school and went to CERN as a kid before they opened up to the tourists, which is very interesting. And just it's a more practical question. Now that you read a lot about Elon Musk and Jeff Bezos getting into space and dramatically reducing the cost of everything, is that something which is going to be, do you think, going to be able to impact on how you do physics, and whether you can start building smaller, maybe less efficient, but more numerous experiments so that you can more quickly cycle through the rate of discovery and failure?
So absolutely. So I'm personally really excited at what's happened with launch vehicle capability in the last few years. That the cost per kilo to get things into space has dropped dramatically. And what this means, this has got several impacts. One of them is that when the launch cost was a substantial fraction of the total cost of doing a mission, it meant that you were very strongly biased to doing experiments that were as small and lightweight as you could make them. And now we're opening up the corner of phase space where you can take larger things that might be fairly simplistic, but it's no longer prohibitively expensive to get them into space. So, for example, if I want to study energetic particles, cosmic rays in space, what you really want to do is to launch, the equivalent of large crystals. So, like, I'll call it a large block of salt as your detection medium. And with the launch capacity that we now have, at the cost that we now have, it's in fact feasible to, say, take a very large block of material, put some instrumentation on it, and make very innovative measurements of cosmic rays in space in a way that would have been, wouldn't have even been contemplated 15 years ago, because the cost to get that mass into space would have basically said, this is just not good use of launch capacity. So it's changing our thinking in what we can put in space. I hope that we start to make a transition to being less risk averse. That I think it's harmful to be in a mindset of failure is not an option. I think that you have to be able to fail, because if you are afraid to fail, it means you're also afraid to take real chances and to do real innovation. And I think if we could start to have more launches and more things going into space, that maybe it doesn't have to be front page news if if an experiment doesn't work exactly as happened, if you still learn from something that fails because you know not to do that again.
So thank you so much. Thank you so much to both, to Julie and Maria. I'm going to draw curtains now here. I really, just from my own point of view, really enjoyed that talk. Something completely different for me. I'm sure I'm not the only one to have been intellectually challenged by everything that you've spoken about. I'm happy that that we've recorded this, so I can go back and listen again. But Julie, thanks so much for taking the time from Colorado there, and Maria for interviewing Julie. And wish you all very well. And next Thursday, Chris Wilkins, who's on this call, is going to be in conversation with Rory Stewart. And so I hope very much you will obviously receive invitations for that, but I hope very much that you'll join us for that. And for the moment, thank you very much indeed, and have a good evening, have a good day. Thank you. Thank you.
Thanks.
Thanks,
Bye-bye.
sir. Bye.
Bye-bye.